for me to really present the work and get probably the most critical feedback from you. So today I'm going to talk about trustworthy algorithms in machine learning. I will try to give first a broad overview of how I see things and why we need this. And then I will talk about one specific work that came out recently from our group that tries to address one part of this. So let me start. And needless to say, please interrupt me if you have any questions at any point. You can unmute and ask. I don't think I will be able to monitor the chat, but yeah, please unmute and ask. Okay, so the very first part is, if you have not seen this before, I just wanted to give this very brief thing, is what we do at ETH in the biomedical image computing group is, we know that the patient comes in, certain tests are applied, and then they're sent to these fancy machines and a beautiful image comes out, which is read by radiologists, a report is written, and which is then sent back to the doctor. And what we try to do is we try to automate this process as much as possible to make things more efficient. And recently, we're also trying to get into this line of actually integrating patient information other than imaging to create a bit more useful clinical decision support systems. So just to have in mind some of the maybe keywords that happen in our group are given on the right-hand side with different colors. So there's a large component of machine learning and Bayesian modeling that happens in the group. And most of the time, the applications, actually almost always the applications are medical imaging, either reconstruction, outlier detection, or segmentation. For visual memory, this is kind of what we try to do. On one hand, we have the reconstruction algorithms. We want to create faster and less invasive imaging, obviously. Related to that, we try to come up with algorithms that can detect what shouldn't be there, as well as the radiologists, and we fail miserably in that. And we try to create algorithms that are really robust and that can be applied in various images without any problems for image segmentation, but also for other pixel-wise prediction tasks. So maybe I should give you an idea of why I'm actually even working in this field and why we need these. So these numbers and these plots are coming from OECD, and I basically retrieved these plots a couple of weeks ago. On the left top part, you have the evolution of the number of doctors per 1,000 inhabitants for different countries over the last 20 years. And this plots does not really say it's only the radiologists, it actually says all doctors. These plots show the same evolution in, again, different countries. But this time, they are MRI and CT exams. And I think it's easy to notice the discrepancy here. Number of doctors, and again, these are the generic doctors, are increasing maybe, I don't know, a couple of % every year, while the MRI exams and CT exams have more than doubled in most countries over the last 20 years. Now, this is probably still fine. I guess if you're a radiologist, you already have experienced this quite a bit. Like this actually puts a pressure. And the last figure probably that complements this is this percentage of elderly in the population in exactly the same countries. The steady increase in the percentage of the elderly means that there will be more and more and more patients. I mean, if the entire population always stayed at 20 years old, probably there wouldn't have been so many MRI and CT exams. But given the current conditions, these 4 plots basically tells us that we're kind of moving towards a insurmountable pressure on radiology departments, and something has to be done. And this is actually, I mean, this is not right now coming only from engineering or computer science departments. This is actually the conversation happening in the radiology, right? If you look at the top radiology journals, Radiology, Journal of American College of Radiology, the current topic is how do we integrate machine learning models in medical imaging in a meaningful way? How do we actually make proper impact? How do we actually prepare data for these things? And the applications, they are there. You know, they're not mind-twistingly complicated applications. We're still trying to automate the laborious tasks that happen. But we're at the point where actually algorithms work okay. We can actually detect or segment lesions. We can detect structures accurately, reliably. We can fuse data. We can detect structures that shouldn't be there, that are suspicious, quite nicely. So, I mean, things are happening. That's pretty impressive. That's one side of the picture. The other side of the picture, where actually is less told, is actually there's a very much dark side to this thing. Now, there was this Nature paper that people tend to cite quite a bit for the success of machine learning, where authors claim that they can actually do, human level detection of suspicious cases and breast screening. And, they basically say that, hey, like the algorithm is able to do quite a number of things and so on. And yet there are still some cases where it seems like all experts kind of find, but the AI misses. Now, if you actually want to create an AI system, you probably don't really want this to happen. I mean, it's okay if a radiologist or if an expert misses a case and the AI system doesn't, but it's really not okay if the radiologist or all experts agree that it is suspicious and the AI system kind of misses it. Maybe this is still okay, and that can be thought of, okay, you know what, these are just algorithms, they can make mistakes as well. Actually, the problem gets larger if you look closer to the data that's presented in that paper. So they basically took two different tests. One of them is they basically built the entire algorithm in UK, and then they sent the algorithm to USA. First, they basically used exactly the same algorithm, and then they tested how well it performs. These are the ROC curves that were obtained in UK and USA. And you'll notice that there's a huge difference. And this huge difference they attributed to the population change. Now, it's definitely interesting. I would argue that probably the population change between the UK and US is probably much less than a population change, for example, going from UK to China or UK to Africa. So actually, it actually shows that the algorithms are maybe a way too specific for the populations that they're trained on. But what is actually even more interesting in this paper is that they have a very large imaging set that they actually do train and they test, and that's fantastic. What is kind of hidden in the article is that 95 or 98% of the data that's coming here, they are all acquired from exactly the same vendor's machines. Now, this is interesting. And they say that generalizability to other data is future work. Sure, it's future work, but it ends up being one of the most difficult type of questions. So effectively what this means is, even if you have the computation power and the expertise in Google, apparently it's not very feasible still to create algorithms that I can take right now and they can basically ship everywhere and use it. So that's still kind of a target that we're trying to attain, but it seems quite challenging. So what does it mean? Some examples, for example, in our latest work for basic image segmentation, and these are segmenting prostate glands in MRI. What I'm showing you here is two different sets of images, one with endorectal coil, but acquired with slightly different acquisition protocol than the training set, and one, an image acquired without an endorectal coil. Now, both of them were not used for training. And these data sets are kind of differ slightly in intensity characteristics as to the training set. Now, the algorithm should be able to predict ground truth, that's shown in the second column, but instead it predicts the third column, which is obviously, it's kind of quite a small part for prostate gland. So simple segmentation method that we try to do kind of fails if there are changes in the scanner, in the vendors, in the protocol, like the accuracy degrades substantially. In another test we've done actually with Olivia Donati, again on the prostate, was we were trying to figure out if we can actually write an algorithm that will look at, for example, the structural images and the diffusion images, and decide whether DCA is required or not for the subject to be able to reach an accurate diagnosis. And we're able to write an algorithm that actually reached an AUC, an area under the ROC curve, of 0.88 using data that was acquired in USA. Okay? And now we basically tested the same system. And this is basically trained on about 300 subjects and tested on 100 holdout subjects. So it's actually reliable numbers. And then we basically took 30, 35 subjects coming from this other site in Wollishofen. And the algorithm kind of did much worse. Instead of 88, now we're at 73 AUC. I hope this is actually enough evidence that actually the algorithms we have right now kind of, they're nice, and in controlled settings, they perform really well. So that's extremely motivating, but they're very far away from what we should, or we can actually trust. And that's an interesting point. Now, from where I stand, there are really four different aspects to trustworthiness in a machine learning algorithm when it's applied to medical imaging, but also for other critical applications. So one of them is it should be robust. So despite variations in imaging conditions, and note that these are small variations in imaging conditions, it should not really fail miserably. Second, it should be self-aware. I mean, the algorithm should basically identify these cases that it has never seen before, and therefore cannot make really a decision. And this is really far from the case right now. I mean, the algorithms, if they're trained to distinguish between cats and dogs, and if I show a giraffe, they will be extremely confident whether it's a cat or a dog. And that's a simple case. Maybe you can actually write a giraffe detector to identify that. But if I now have an algorithm, if I now have an image that's actually full of artifacts, actually it doesn't have to be full of artifacts. Let's assume that it's actually, there are enough artifacts to mask the evidence that you want for a certain task. The algorithms will make a decision. And that's really not how it should be. A human would not do this at all. The algorithm should be risk averse, meaning that in most medical applications, I mean, you know this a lot better than me, but there are certain type of mistakes that have severe consequences. Right now, we're all aiming to increase the accuracy, but maybe that's not a very good idea. Maybe actually what we should be doing is to reduce the risk of making such mistakes. Effectively, all of these algorithms will be operated at a point where you have very high sensitivity, and they only become useful if they reduce the false positive rates, right? I mean, an algorithm with great false positive rate at a low sensitivity would really be useless. So how do we get that? And the last part is the transparency. I mean, this, everyone talks about it, this interpretability and so on. And it's really a difficult topic because the definition of what it means to be transparent or interpretable is the missing part. So today, I mean, I can talk about all of these for hours, but today I will actually focus on one specific part, the robustness, because that seems to be one of the easiest questions that we can answer, despite being difficult. So I will go through this paper that was published beginning of this year in medical image analysis, and we named it as test time adaptable neural networks for robust medical image segmentation. So I will give a brief definition of what's there, of the problem, currently what's available, give you the algorithm and then the experimental results. And there will be parts where it's kind of math heavy, so I will use notations, but I will try to explain everything as much as possible. So you should ask questions whenever there's something unclear. So maybe this might be actually an interesting point to stop and ask if there are any questions so far. Perfect, okay, so I'll continue. So before doing this, I should basically thank the funding sources, the CSCS, the PHRT, and then the CRPP of Artificial Intelligence for Oncological Imaging, which is actually headed by the larger group at ETHZ, and the people who actually made this possible. So Nirav was the lead author here. Ertunç, I think he already gave a lecture last week or the last time here, and Krishna, who was also involved in this work. Excuse me for the resolution of the images. Somehow my Mac updated and now I'm unable to get back high resolution images. Anyway, so image segmentation is a well-known problem, right? The idea is you have these images and you want to be able to assign classes to each pixel based on the intensities. So given an image like this, you want to be able to get the segmentations, either certain areas or different structures. And here I show you brain MRI, prostate MRI, and cardiac MRI, with the, a lot of structures in the brain, the glands in the prostate, and several structures in the cardiac. Here I only show one of the ventricles. Now the main idea is, right now I think it's well accepted that you build a deep neural network, and for a variety of the anatomies, it works with minimal modifications out of the box. Actually, if you actually apply this model in these applications, you get dice scores that are somehow on the order of 0.80 or 0.85. Now these actually kind of doesn't make much sense without a baseline. So the best baseline is that the segmentation accuracies are claimed to be close to inter-rater variability. Actually, we did this study with Anton when he was at USC still. We basically asked 6 people to segment prostate gland of 80 patients. And then we computed the dice overlap between between these readers. And on average, it was 0.74. So I think for certain applications, definitely the prostate MRI, the algorithms are as good as radiologists or within rater agreement of radiologists in these cases. Now, looking at these numbers, I think we can all say that, okay, this is a solved problem. So I don't really have to talk much about it. And I wish this was the case, but it's not quite there. Actually, if I train an algorithm on a certain set of images, for example, given by these things, and by the algorithm, I will always represent it with this box called S theta, which stands for segmentation, and theta are simply the tunable parameters of the algorithm, so the knobs of the algorithm. So when I train an algorithm with the source domain, they perform fine. And now if I go on and apply these algorithms on images with slightly different characteristics, or maybe very different characteristics, but effectively showing the same structures for a human, segmenting T1 weight or T2 weight image of the brain is not very different. The algorithms are not giving me the ground truth segmentations, but rather giving me segmentations that are not very useful. Now, when the changes in the intensity characteristics are small, then I see that the segmentation is fine despite some errors. When the difference is large, it completely fails. When I use a different coil apparently for certain structures, it actually doesn't get the structure right. So even slight differences between the statistics of the intensity characteristics.
Co? Bierze, szuka ptaka teraz, bo tylko dawać tam krzesło, tam było krzesło i tam nie wiem, gdzie on jest. Aha.
Okay, so I will continue.
Oh, I'm sorry.
No worries.
Mute the microphone. Thank you.
So, so effectively, the point is, even slight differences between the statistics lead to substantial degradations. And this happens, as I showed you here in segmentation, but actually happens in classification problems as well, as I discussed previously. Now, I wanted to give some numbers for these things. And these are dice scores for the 4 different structures that I talked about. I have the brain, the prostate, and the heart. And we looked at different prostate segmentations, parts, one as a whole gland and one as separate glands of the central and the transition zones. And if I train an algorithm and test it on the same domain, I get good accuracies like I've shown. So this line here, what's called ST, is called the source domain, meaning that I train and test the algorithm on images coming from similar acquisition protocols, the same vendor, the same scanner. They work well. If I take this algorithm and now apply it to images coming from different domains, which are called the target domains, which are acquired either with different protocols or with different vendors, then the accuracies drop by a large margin. So target domain 1 here is this other T1 weighted image. Target domain 2 here is this T2 weighted image. And for the prostate, the same thing. I think one of them is the case with the endorectal coil, one of them is without the endorectal coil, and so on. Now, the issue is these images, they're not worse than the other ones. Actually, if I build segmentation algorithms that are trained with those images, I know that I'm able to get good segmentations like the row that's shown here in the second row. So I know that algorithms are possible to segment those images clearly. But if I actually apply the source domain images, I'm really far away from them. And that's kind of the essential problem here. And this is, I mean, needless to say here, but it's common in MRI. And it's even common, even if you do a software update. Sometimes if you're unlucky, the intensities change and then the segmentation algorithm starts failing. So obviously this problem is big and there has been quite a number of efforts to solve this. And one of them, and I will talk about a few of them, and then I will give you the algorithm that I was talking about. Okay, so very simple notation. I will mention or denote images as X and segmentations as Y. And as I said, the segmentation algorithm is denoted by S theta, theta being the parameters. Okay. So in this case, I will talk about deep learning models. So it's a segmentation network. It's a function that takes in images and spits out segmentation maps. I will denote a source domain training set, a set of images, set of cases where I have the images and pixel white labels, and they're all acquired with the same protocol, so they're called the source domain images. And I can define a loss on them, meaning that it's a loss that actually looks at the ground truth segmentations, looks at the predictions of the neural network, and computes the difference between them. And by training the algorithm, what I mean is I basically find the best parameters that will reduce that loss on the source domain. And now I'm happy. Using the best parameters that I figured out, I can actually feed any image here and get out the segmentations. For the target domain, I will actually represent them again with X and Y, but I will use sub TD for the target domain. And here I will assume that there are, again, images. So source domain images are coming from a space of images. Target domain images are coming from another space of images. And the issue is they're not the same space. But the labels themselves, they're coming from the same space, meaning that I'm looking at the same anatomy. Not exactly the same anatomy, but the same anatomical site. So I expect to see brain images, brain structures. I expect to see prostate and so on. Now, mathematically, the assumption that neural networks will generalize says that if I actually take the network trained on the source domain, but feed in an image that's coming from a target domain, the output should be a good segmentation map. And that's the thing that fails. Okay. Now, what are the possible scenarios? And how can I actually address this? The very first thing that I can do is I can say, hey, you know what? Let's actually forget about this problem. Let's say that I have this algorithm, and whenever I deploy the algorithm at a certain site, I basically acquire training data there and simply train different instances of the same algorithm. On the source domain, I basically train it with respect to a loss defined on the source domain. On the target domain, I define it on target domain. And this is a good strategy, and then it will give you good results all the time. The issue here is every time you apply the algorithm at a different place, you need a different set of images and a different set of labels. And this creation, that costs money. That actually costs a lot of time as well. So I can give you one example. For example, lately we basically segmented, asked for segmentation of 30 lumbar spine MRI. Each of them had, the T2 weighted images, and I think each of them had roughly 20 to 25 slices. And we basically asked for segmentation of multiple structures, so almost all the structures that are visible there, and it costed roughly 10,000 francs. And that's a huge price if you want to ship the algorithm to many different places. The other option is to do transfer learning, right? Instead of having, large number of samples here, I can maybe have few samples and then try to transfer learn the examples, the network, meaning to fine tune the parameters. And this is a good strategy as well, but I still kind of need samples, and that's not nice. What I can do is unsupervised domain adaptation, meaning that, I have these source domain images, my data set that I create in the first place. I can simply ship it to different centers. And at those different centers, I can retrain the algorithm. And that's a very good approach, actually. But the issue here is that shipping data is kind of a no-no as far as I understand. Now, a good strategy that actually does not have any of these problems is what's called domain generalization. So what I do here is, on the source domain, I try to minimize the loss. That will both make segmentation good, but also it will extract features that do not necessarily depend on the specifics of the contrast. How do I achieve that? I basically really use a lot of data augmentation for each source domain image and ask the network to extract both, do segmentation well in all of these cases, but also use features that do not really or cannot tell me that these images are coming from different contrasts. Kind of a contrast ignorant feature extraction. And then I go to each target site and I simply apply the algorithm. And that's very neat. Although this is not really complete, as I will show, a better strategy would be to say, hey, do that, create kind of these contrast ignorant networks as much as possible. But then when you ship the algorithms, adapt them as well. Basically adapt them with respect to the contrast that you observe at the target domain. Now, just for completeness, there is also another set called unsupervised segmentation, meaning that if I have a very good understanding of the anatomy, and if I can build atlases of the anatomy, then actually I don't really need these learning tools. I can actually go ahead and segment that image through atlas-based registration and so on. The issue is these type of algorithms work well for certain anatomies, and then they don't work for other anatomies. So for me, domain generalization is the preferable option among these. And there are really two different variations. One of them is a training strategy, and the other one is an inference time strategy. So let me give you an idea of what they are. The training strategy looks something like this. So again, in my source domain, I have a space of source domain images, and the image that I see here is just one instance there. I will feed it to a segmentation network, and I will get a segmentation, which is a proper prostate segmentation, which is an instance in the plausible set of segmentations, meaning in the set of realistic prostate segmentations. Now, when a target domain image comes in, it actually has a different space. So the example that I see here is a different instance in that space, and it doesn't have an overlap with the source domain. So what happens is if I now feed this into the network, I get a segmentation. That's now it is a segmentation. It's just not accurate. It's not just a realistic prostate segmentation, meaning that it is a segmentation. It's just not in the plausible set. So now one strategy is to do data augmentation. And by that, what I mean is when I train this algorithm, as I said, I try to, transform the images by random intensity transformations, random geometric transformations, such that I try to artificially expand the space. And I hope that actually this extended space kind of overlaps with my target space. So that in this overlap, in this intersection, my algorithm will perform well. Now, this is a heuristic method, obviously, but it provides a very, very strong baseline, as I will give numbers shortly. The performance here obviously can be improved if you actually think about, for example, other strategies that will extend the space in specific ways. If you have certain ideas about the target domain, then you can use that too. Now, the other very famous method is what's called the meta-learning. So instead of having one source domain during training, you will assume that you will have images from multiple source domains. And then you try to make algorithmic updates using only, for instance, two of these source domains at once, but ensure that that update will also increase the accuracy of that third source domain. Effectively, I try to basically extend the combination of these source domain images and train the algorithm. Now, numerically, what does it mean? So these are the numbers that I get from applying those type of algorithms on the data sets that I used before. So here I have 3 meta-learning algorithms in the top 3 rows. And in the last row, I show you a data augmentation algorithm. I see several things. One of them is all these algorithms seem to actually improve the accuracy on the source domain itself. So effectively, what happens is that adding these robustness features kind of seems to improve the generalizability of the algorithms in the source domain. But more importantly, I see that all these algorithms kind of improve the accuracy of the networks on the target domain. So they do the task that we want them to do. So for example, for the brain in target domain, we go from 59 to almost 75. For the prostate, the same thing, we go from 59 to 77. For the heart, we go from 67 to 74. That's actually fantastic. Well, when the domains are very different, they seem to fail, but maybe that's okay. That's kind of reasonable. Now, take-home message is training strategies for domain generalization really improve performance, so they're great. But maybe important thing here is like all these kind of complicated meta-learning algorithms, they're good, but even the simplest data augmentation method seems to work wonderfully well and possibly better than the other ones for these data sets. So it's actually surprisingly effective. However, there's still a gap to close. We go to 75 and not 89. We go to 77 and not 81. So how can we close this gap? Next, I will talk about a way to close this gap further. But before that, maybe I should stop and ask if there are the questions.
Yes. Thank you.
Try to move quickly. So the algorithm that we're trying to say is, hey, this is a good idea, but then augmentation might not be enough. Right? You wouldn't be able to segment if you don't know how to augment it, as Andreas eloquently put it. So the idea here is basically you want to say that, hey, the idea, the hypothesis that we came up with is that actually if you want to generalize, you really want to adapt the algorithm as much as possible for every given image. Effectively, what you want to do is, for this image, for example, which was the data augmentation was not able to capture it, so the segmentation result is quite bad. What you want is you want to adapt the algorithm such that you push the segmentation inside the plausible segmentations. And there are really two questions here. First, how to derive the adaptation, and the second, what parameters should you adapt? Now, what we want to do is, first of all, we want to drive the adaptation such that we really want to push the segmentation results into the plausible set. So again, we will adapt this network, push it into the set, making, in theory, the segmentation result more plausible. So how do we actually do it? We define a prior distribution through what's called the helper network. And for that, we use a denoising autoencoder. So effectively, what it does is it takes into account the segmentation and then tries to project this onto the plausible set of segmentations. Now, if the segmentation is already in the plausible set, meaning that it is actually a segmentation that I can get, it is actually a really interesting or really possible process segmentation, then the difference between these, the input and the output, should be 0. If it's not, then the output or the difference should not be 0. So we use this output, the difference between the input and the output, to this denoising autoencoder, the helper network, as the main cost to drive the adaptation process. Okay? The crucial point here is, you see this segmentation space is invariant to the contrast. It's actually, it doesn't really care what the image contrast is. It can actually be trained. I can train a model in the source domain without really making any mistake in any given target domain, because this is shared across the target domains. And you can actually do what concurrent work proposes to say, hey, you can actually do the same trick, not on the segmentations, but on the images. And that's a good strategy, but then you inherit some of the problems here. Like the intensity itself are not ignorant to the contrast. So you will have some troubles in defining the same strategy there. Okay. The second question we want to ask is which parameters to adapt. There are really 3 options there. One of them is you can adapt the entire system. You can adapt a small set of the parameters, or you can append something shallow before the segmentation module and only adapt that. Now, the first one is really nice and it can work, but then it would actually change the segmentation too much, so much that it will ignore the image and simply create a segmentation with which the helper network is happy. Second, you can say, hey, I can actually, adapt a small set of these parameters so that the segmentation cannot change too much. And that's a good idea, but then these parameters are kind of your investment, right? You paid quite a bit of money, quite a bit of effort to optimize these parameters, so you don't really want to lose them. And the last one is what I call, you can adapt a shallow module such that the images will not change. The segmentations cannot break off from the images. I keep the valuable parameters I have, and I get a good segmentation accuracy. Now, I'm not going to be able to go into the details, but let me simply give you the results here. So these were the results, again, numerically. And what we show here is, in almost all the applications, we can really improve the segmentation accuracy with a large margin and closing the gap even further. And this even happens in cases where the target domain intensity characteristics are wildly different from the source domain. And again, it doesn't have to see it. It will be able to adapt itself and try to get a good segmentation out. And the moment where it's able to not get a good segmentation out, meaning that, I take the segmentation that I got and I made it as good as possible. And when I project it, it still somehow errors. And that's the point where you can say, aha, okay, this is actually an image modality that I cannot adapt to, or there is something else going on in this segmentation. Visually, what it looks like is what I'm showing you, and this is the last thing I will show, is you have the image on the left and the ground truth segmentation on the right. In the second column, this is what happens if you use only the source domain trained neural network and apply it on the target domains. So you see that the segmentation maps seen on the second part here are the ones that I showed before, so they're not very good. If you do data augmentation, you can actually recover a bit. So you can, for example, make the first segmentation quite nice. It kind of starts failing again if the target domain is far away from the source domain. By the way, these images are the normalized images, meaning that even if you want to use a normal neural network, you have to normalize the images to some intensity ranges. And these are those normalized images that the networks see. What I show you here on the third column is the result of the algorithm that I showed. So basically, the algorithm automatically adapts itself, meaning that it takes this image and converts it into this contrast. It takes this image, converts it into this contrast, which somehow looks similar to the top one. And those contrasts ends up being what the neural network wants to see, and it's able to segment them accurately. And the same thing with the prostate. It takes both of these images and maps them to a similar contrast. The funny thing is, to the human eye, these images are not very high contrast images, but somehow that's what the network wanted and is able to segment accurately. And with that, I actually want to end, given the time. So my final conclusion is, so there's still a gap to close, but I think it's a fantastically interesting question. And it's an exciting question because it links to the much larger question of generalizability of machine learning algorithms. Thank you. I think Mikhail has a question.